Hello everyone, welcome back to the SWAM NPTEL course on engineering aspects of biofuels and biomass conversion technologies. I am Professor Ijaz Ahmed, currently Assistant Professor in the Department of Chemical Engineering at IIT ISM Dhanbad. In Module 6, we are discussing about the pyrolysis of biomass. Particularly, we discussed about the high temperature conversion technologies, we discussed about the pyrolysis, the types of pyrolysis, how to develop the process flow diagram. Now we'll discuss about the types of different pyrolyzer and the bio-oil upgradation in this unit. If you remember in the previous class, we discussed how to develop the process flow diagram. So we started from biomass, we went to desizing, drying, grinding, feeding, then pyrolysis. And then the gas cleaning, condensation, and then the reutilization of gases and the char. So this is like here, it should go like this. Okay, so this is what we used in the biomass pyrolysis. So, but the problem here is that the bio oil that we get has some challenges. Okay, for example, if you go for a fixed bed, a fluidized bed system, then you will see that the feed enters here. So this is a different arrangement than the earlier that you have seen. That was mostly a fixed bed. So there will be little change, but the feed, this is my fluidized bed system. There is the carrier gas, which, and this is grate or distributor plate, you can say. I would say distributor plate. The job of this distributor plate is to distribute the air uniformly here. The feed is coming. Now this feed may have some pre-treatment unit, like I said. You will have conveyor. Prior to that, you will have grinding. Prior to that, you will have sizing, or you can have drying as well. Prior to that, you can have desizing. Prior to that, you can have collection and sorting. So this is something how you can make it. Okay. So herein, let's say this is, the fluidized bed pyrolyzer with electrostatic precipitator. Now here in this case, the carrier gas enters from the bottom and then it will go here. Initially it will try to pass, but if we keep increasing the velocity of the carrier gas, what will happen, it will start pushing this up, and then there is a minimum critical velocity or minimum fluidization velocity. If that is achieved, this will start floating herein, and the gas will, whatever the thermal cracking will happen, let's say this is my hot gas. Okay, so whatever the cracking is happening, those vapors will pass through this. We can have the vapors passing through the cyclone separator. So this is cyclone separator, as I told you earlier, and in this the char with and ash will get removed, and this char can be sent to a char burner like I showed you earlier, and this the PM free vapors, particulate matter free vapors, will go to condensation where you will get the bio oil, which is a heavier fraction, and then again we can put a second condenser, we can get the bio oil, which is a lighter fraction, and then we can get the non-condensable gases, some part of which can be sent to burner here, that can be burned down to provide the heat energy to the fluidized bed pyrolyzer. Okay, so like this is a typical flow. Initially the carrier gas is entering here to the fluidized bed reactor along with the biomass feed, like feed is entering from here. Then at the second stage the gas exits the reactor and passes through cyclone. This is cyclone, then series of condensers. Okay, where char and ash are removed and product is sent to the this char burner. The clean gas flows to a quencher, these quencher, and to recover the heavier and lighter bio oil. Now after that, once the remaining gas is moved to a condenser where we get the lighter fraction, as I said, then non-condensable gases are directed to a either here to a boiler or to a burner, and then it provides a heat that can be recycled as carrier gas. Instead of this, we can use this as carrier gas. Okay. Now, this is how. Let's say if I have a different configuration than this, then what will I do? Okay. Or why should I use the fluidized bed system? Okay. So the primary advantage of fluidized bed, as I told you earlier also, that it has uniform temperature and excellent heat transfer. Because the particles are moving here, it is getting heat from all the direction, all the surface area is exposed compared to the larger particle size. Okay. It has high bio-oil yield up to 75% and moderate construction and operational complexity. The scale up is very easy for larger capacities, but the problem with this such kind of pyrolyzer is it requires a small feed particle size, because then only it can get fluidized or flow. Okay, the minimum fluidization velocity depends on the particle size as well. Therefore, lower particle size are preferred. The operating cost is high, definitely. Now, the other kind of pyrolyzer we have is the circulating fluidized bed pyrolyzer. Now, instead of, what you can say, getting this heat from the gas burner, what we do that we use a heat carrier here. So everything is same. So this is my fluidized bed system. The feed is coming here. The carrier is gas is going from here. It will fluidize. It goes to the particulate matter. But here the heat is going through another thing. So what we do, this is like we have sand here or some any other gas. This is heated and this goes in here. The carrier gas takes the sand and biomass. After fluidization, the sand comes here, and when it hits the walls of this cyclone separator, so this is cyclone separator, the particle will fall down. The char and heat carrier will come here, the sand, and the particle free or particulate matter free vapors will go here. Then, as I said, we had quencher 1 to get the heavier bio-oil fraction, and then the further clean gas is condensed to get the lighter bio-oil fraction, and then we have clean non-condensable gases. Okay. Now this clean non-condensable gases can be recycled here to burn this char, and as well as it also produces heat, and that heat is taken by sand and then goes here in, and the ash is removed from here. Now to burn this non-condensable gas, we also need secondary air, so which is provided from here, or some, if all the gas are not used because you produce lot of gas, so part of gas is only given here. Most of the gases goes to the boiler for heating combustion. Okay, some part of gas can also be recycled to be used as carrier gas here. Okay, so and then from here we'll get the flue gas that will go with the treatment, and then we can get this. So if you see, typically the carrier gas enters from the bottom of the pyrolyzer and leave from the top. The biomass is fed directly into the midway into the pyrolyzer. The product gas exit to cyclone, where char and the heat carrier, which is sand in this case, is get separated, and then char and sand are sent to this burner, where the sand is again reheated and returned to the fluidized bed pyrolyzer. Okay. Now the ash is also removed here, you can see, and flue gas exits from this burner and directed to the heating unit. The gases from this goes to this, as I said, to get the heavier bio-oil fraction, light bio-oil fraction, and then we get non-condensable gases, out of which major part goes to the boiler and heating unit. Some part is recycled as a carrier gas here, and some is recycled like for the burning. It has similar advantage to like that of fluidized bed, good temperature control, efficient heat transfer, can process medium-sized biomass particles larger than the conventional fluidized bed pyrolyzer requirement. Okay. But the disadvantage here is that it requires large quantity of heat carrier, for example sand, and then it is more complex in operation compared to the fixed bed or simple fluidized bed pyrolyzers. And because the sand has to be moved from here and here, lot of complexity is there, so it has high operating cost. The other kind of pyrolyzer is the rotary cone pyrolyzer. Okay, now this rotary cone pyrolyzer, as you can see here, this is a motor. The biomass is fed from the bottom, heating is done from this side. Okay, so biomass enters the feed from the core, heat is applied from this outside walls of the cone, and a motor spins the cone. It generates the G forces that create swirling motion of particles and gas and condensable. So when after thermal decomposition, the gas and condensable material moves from here. Okay, the char and ash also exit from the top along with the vapor. Okay, that means we need to again use the cyclone separator here and other things. Okay, now the advantage of such kind of unit is, one is compact design, simple construction and operation, the low requirement for heat carrier material. As you can see here, there is no heat carrier material, but the major problem is, like, if it is compact, it will be of a smaller size, so limited processing capacity, requires fine particle feed for efficient operation, and difficult to scale up for large scale production. Okay, the other kind of pyrolyzer is auger pyrolyzer, or we also call it a screw kind of pyrolyzer. So you can see this is a screw, this is a feed hopper, you can say feed hopper. The biomass is fed from here. The screw moves with the help of this motor. This motor is connected to a variable fluid drive which rotates this screw, and when biomass falls down, it moves here. It can have one zone complete similar heating, or it can have different heating zones. Let's say zone 1, zone 2, zone 3. Okay, so heat can be given by electrical or the combustion of gases. What we get is here the condensable vapors and then char and ash. Okay. So the design, it is a heated cylindrical chamber containing rotating cork screw auger driven by a motor. As I said, the feed enters from here, from the one end of the cylinder. The auger moves the biomass, as I explained, that along the heated walls, and then condensable vapor exits from the top outlet while the char and ash move from the bottom. So this is one way. The other is you can also put here and then take the vapors out. Okay, it operates at low process temperature around 400 degrees Celsius. Now the major advantage here is that it can be a continuous process, it's compact design, simple construction and easy to operate. But the disadvantage is it requires long residence time, so the movement is very slow. The lower bio oil yield and higher char yield, because it is slow process, so more the residence time, more is the char yield. Okay. Now, scaling limitations due to restricted heat transfer efficiency. The other types of common pyrolyzers are like ablative pyrolyzers, as I said, vacuum pyrolyzers, entrained flow pyrolyzers, etc. So, if I make a typical comparison of this all kind of pyrolyzers that we have. So fluidized bed, uniform temperature is important, that is to be noted. So that causes good heat transfer. Higher bio yield up to 75%, easy to scale up, but it requires a small particle size that increases the operating cost. High inert gas consumption, high operating cost. While in circulating fluidized bed, we have the advantages like this. It can handle the medium particle size, okay, or medium sized particles. It requires large quantity of heat carrier. This is the major disadvantage, and because of that, it becomes a very complex process, and the operating cost increases. Okay. Similarly, we can have rotating cone, which is compact and simple in design, low heat carrier requirement, but it cannot be scaled up. It has very limited processing capacity and required fine particles for feed. Okay. If I talk about the auger, it is compact and easy, operate at lower temperature, but requires long residence time, lower bio yield, and high char yield. And also difficult to scale up because of the poor heat transfer. Mostly the heat transfer here happens via the conduction. Okay. Other are like ablative, vacuum, intent flow. I said they have niche application, but they are not widely used or developed for large scale operations. Okay. The oil that we get, I have already told you, it is similar to heavy fuel oil, but with a difference in oxygen content, and because of that, there is a difference in heating content, and also in the pH value. So the bio oil that we get are the this. Now, if we have to remove, as I said, that this oxygen, if we remove, we can improve here. So if I reduce this, I can improve here, and I can also I have to neutralize this. So that means we have to upgrade this bio oil if we want to make it even like heavy fuel oil. Forget about using in the engine. Using in engine definitely requires a hydrocarbon range fuel, but even if you want it to use in the boilers, if it is acidic, it will corrode the boiler. Okay, so what we have to do, and then there is oxygen, so low calorific value. So if we remove the oxygen, we can do it. So there are different types of upgradation methods. Some of the methods are like we'll discuss one or two process flow diagrams, but primarily the bio oil from pyrolysis is a complex product, and that contains water, oxygenate, acids, and solids. Okay. Now this has in fact very high oxygen content that causes, as I showed you, 30 to 40% oxygen content, and because of that the heating value is very less and there is a chemical instability, and then upgradation is needed to improve the fuel properties, particularly to increase the energy density, reduce the corrosiveness, improve the storage stability, make it compatible with the conventional fuel, etc. So like I said, how you can increase the corrosiveness, we can neutralize it. If we remove the oxygen, it becomes more stable. So when if we remove the acidity, it becomes more stable. Then we can improve the storage stability. Otherwise, as long as it is acidic, it can go under self-catalyzed reaction, and then we cannot store it for a long time. So if we neutralize it, we can go. If we reduce the oxygen, we can make it compatible with the conventional fuel. We can increase the energy density as well. Okay. Now, some of the processes are like hydrodeoxygenation, etc. But because it is so complex that there are so many problems. One is the high water content. Okay. The acidic pH, which is corrosive, usually the high viscosity and tendency to polymerize during a storage because of the self-catalyzed reactions that happens during the process. Okay. Similarly, the presence of solids like char particle ash can cause problem. Then it is immiscible with conventional petroleum fuels. That is another major problem. So these are the factors that requires actually upgradation of the bio oil. Okay, and in this regard, there are different upgradation methods. For example, one is the physical method where we use filtration, centrifugation to remove the solid particles, or we use solvent addition to improve the miscibility and stability. Similarly, we do phase separation to isolate the aqueous and organic fraction. Okay. So this is one of the important methods that we use. Then we go for the chemical method, like we do esterification to convert acid into esters, that reduces the acidity, or we do hydrogenation to saturate the double bonds to improve the stability, or we can use catalytic methods like we can do hydrodeoxygenation to remove the oxygen using hydrogen over a catalyst like cobalt molybdenum, nickel molybdenum, noble metals, or we can go for catalytic cracking that breaks large oxygenates into the hydrocarbons, or we can use thermal methods like mild hydrothermal treatment or thermal cracking, etc. Okay, so now let's say if I have to go for hydrodeoxygenation is a major route for producing drop-in biofuels. Okay, why? Because it removes the oxygen. So to remove the oxygen, we use hydrogen gas plus catalyst under high temperature and pressure up to 50 to 200 bar. Oxygen actually converts the hydrogen get attached with the oxygen of the bio oil to convert into H2O, and then when H2O is reduced, so for example if I have this, let's say, and here I have one oxygen, so this is oxygenate. If I give H2, what I will get? Plus H2. Okay. So that means I can get a linear chain hydrocarbon. Okay. But the challenges here are that there is very high hydrogen demand. The most important part is hydrogen is the cleanest fuel. So we have to use the cleanest fuel to produce a dirty fuel which has carbon. Okay, but then you can't do anything as of now. The catalyst deactivation due to coking and impurities. These are some of the major challenges that happens. Expensive high pressure equipment because high pressure around 50 to 200 bar is required. The temperature is 200 to 400. Then catalytic cracking like that operates at 400 to 50 degrees Celsius without hydrogen. And then we can overcome the limitation of this previous process that we saw here, high hydrogen demand. So if we have to get overcome that limitation, we can go for catalytic cracking that operates around 400 to 50 degrees Celsius, but the temperature is higher than the previous one without hydrogen. Now it uses acid catalyst like zeolite to deoxygenate and break the larger molecules into the smaller one. As a result, it produces gasoline and diesel and hydrocarbons. Okay. Now it has lower cost than the H2O but yields more coke and lighter coke material because cracking is happening. Okay. So that leads to more coking and light gases production. So the liquid yield will decrease definitely when the vapors are getting cracked further. Okay. Similarly, we can have physical and solvent based upgradation. For example, the solvent addition like ethanol, biodiesel that improves the stability and reduces the viscosity. We can have emulsification with the surfactants to blend bio oil with diesel. We can have distillation to separate the fraction of chemicals and fuels. But the problem with these methods that these do not remove oxygen and only improves the handling of the bio oil. Okay. So these are some of the limitations which are there. This is a typical bio-oil upgradation unit. You can see we have crude bio-oil here, and then we use some auxiliary chemicals charged into the pre-reactor where we de-acidify. We do the de-acidification via esterification, etc. Then we pass it through a separator where the separator, the aqueous fraction is removed, and then we have organic fraction. That organic fraction goes through a hydrodeoxygenation reactor where it is converted into hydrocarbon which is oxygen free. So when it comes here, we have like the in hydrodeoxygenation or deoxygenation, the cracking also happens, and there are wide range of products. So we need a distillation tower, distillation column to separate the light fraction like gasoline, the medium fraction like kerosene and diesel candidates, the heavier fraction like fuel oil, etc. that can be further cracked up. Now from here, whatever the gases we get goes to the scrubber, and then H2 is separated which is recycled back here for supply to the hydrodeoxygenation unit, and then other gases are sent for cleaning and separation. While this hydrodeoxygenation unit, as it requires hydrogen for the reaction, so the hydrogen is supplied here from the gasification unit. Okay. So this is a typical process. So what I mean, the physical extraction can be used to separate the compound based on their affinity for a specific fluid. Now especially the phenolic fluids can be removed using the aqueous medium solution like sodium hydroxide in water, or phenol easily dissolves in the sodium solution due to chemical attraction, and then when they are dissolved, the less oxygenated compound remain in the aqueous phase. Okay. So after that, separated compounds can be distilled or can be sent to the hydrodeoxygenation reactor. Okay, and we can see that. Now there are several emerging technologies as well. Okay, so like supercritical fluid treatment, which uses CO2 and ethanol. We have plasma assisted deoxygenation. We have integrated catalytic pyrolysis for in situ upgrading during pyrolysis. So this is all. Thank you. See you in the next.